Let us now learn a new concept, that is sum of n terms of a GP, that is geometric progression. We have learned this for arithmetic progression. What was the sum of n terms of arithmetic progression? The formula Sn was given by n by 2 in the bracket 2a plus n minus 1 into d. That was the Sn for AP. We are going to find the Sn for GP. What is Sn? For a GP, if I say T1, T2, T3 and so on are the terms of that geometric progression, then I can say that the sum of first n terms is, that is T1 plus T2 plus T3 plus so on till Tn, sum of first n terms, denoted by the symbol summation r is equal to 1 to n of tr. Now this summation symbol implies that we have to add all the TRs where R will take the value from 1 to n. So that will be T1 plus T2 plus T3 till so on till Tn. And this summation is denoted by the letter Sn. Now we have to find out the formula for Sn. Let us now see how to find out the value or formula of sum of n terms of a geometric progression. So let us start. The theorem states that if AR square, so on is a GP, then the sum of first n terms of this GP denoted by Sn is equal to A plus AR square, so on till the nth term given by AR raised to n minus 1, which is denoted by the summation as, the summation symbol is denoted as summation of R is equal to 1 to n of TR. And the formula is equal to A into 1 minus R raised to n whole upon 1 minus R, subjected to the condition that R is not equal to 1. So we have to prove that Sn is equal to A into 1 minus R raised to n whole upon 1 minus R for the condition R not equal to 1. So let us start our proof. We have been given that Sn is A plus AR plus AR square plus so on till AR raised to n minus 1. What can we take common from this? We can take A as common. So we have written Sn is equal to A taken common in the bracket 1 plus R square plus dot 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 till R raised to n minus 1. This is our equation number 1. If I multiply equation 1's both the sides by R, I will be getting R into Sn. And the right hand side will become A into R plus R square plus R cube, so on till R raised to n. Now what I will do is I will subtract second equation from first equation. What I get is Sn minus R into Sn. That is, if I take Sn common, it will be Sn into 1 minus R. And on the right hand side, I can see that if I do the subtraction, R and R gets cancelled, R square and R square gets cancelled, and so on all the powers of R, including R raised to n minus 1, and before this there will be R raised to n minus 1, that will also get cancelled. What only remains is 1, which is not getting cancelled, also R raised to n, which is not getting cancelled. So what will remain in the bracket is 1 minus R raised to n, and outside it will be A. So I can say 1 minus R into Sn will be equal to A into 1 minus R raised to n. Obviously, if I take 1 minus R in the denominator, because we have subjecting the condition that R is not equal to 1, so obviously 1 minus R will not be equal to 0. We can take it in the denominator. We get our formula Sn is equal to A into 1 minus R raised to n whole upon 1 minus R. Now that we have seen what is Sn for a geometric progression, let us see some important properties related to Sn. So, some important things to be noted are, number 1, Sn will be equal to A into 1 minus R raised to n upon 1 minus R only when R is less than 1 and R is positive. So the ratio has to be positive and it has to be less than 1. For the second condition where the ratio is positive and it is greater than 1, the formula of Sn is slightly changed and modified to be equal to A into R raised to n minus 1 upon R minus 1. So if you have noted, in the first formula we had 1 minus R raised to n and 1 minus R. Now we have R raised to n minus 1 upon R minus 1. Now, you might be thinking, what will be the condition when r is equal to 1? We have seen for r less than 1. We have seen for r greater than 1. What will be the condition when the common ratio r is equal to 1? So, when the common ratio r is equal to 1, what will be our terms? Let us say our first term is a. We multiply each term by r. R is 1. So, I will do a into 1. So, a into 1 is a. The next term again a into 1 is a. The next term again a into 1 is a, and so on. All my terms of geometric progression will be equal to a. So if I say I am adding a n times, won't that be equal to n times a? Or can I simply write it a into n? So when r is equal to 1, the sum of terms Sn is equal to a into n. Correct? So these are the three formulas for summation of n terms of GP for three different conditions of R. Now one important thing to be noted, my dear students. Whenever we do Sn minus Sn minus 1, the answer is Tn. Let me explain this with a simple example. If we take n terms, so I have taken n terms. Now I am doing addition of n terms. So what is that? Summation of n terms denoted by Sn. So this is sum of n terms, Sn. Now, I shift one term behind. So, I am shifting to n minus 1 nth term. So, nth term I have removed. N minus 1th term I am considering. So, sum of n minus 1th term. That is S of n minus 1. So, this was Sn. This is S of n minus 1. If I subtract S of n minus 1, that is sum of first n minus 1 terms from n terms, what remains is only the last term, that is nth term, correct? I am repeating again, from n terms, I am removing the sum of n minus 1 terms. So, Sn minus S of n minus 1, what remains is this last term is Tn. So, can I hence say S of n minus S of n minus 1 will be equal to Tn. This is a very, very important formula from the point of view of solving questions, solving sums based on geometric progressions. So these are few important points to be noted after you have learned what is Sn for a geometric progression. Let us now see how to find the sum of infinite terms for a GP, that is geometric progression. We have already derived the formula for Sn, that is sum of n terms of GP, where we have derived Sn in three forms, of which two forms are most important, where r was less than 1 or r was greater than 1. So let us see how to find sum of n terms of GP and sum of infinite terms of GP, both of them. Let's see. For sum of n terms of GP, the formulas that we had derived were, the first one was for a GP of positive terms. So here we are considering GP of positive terms because we are further going to find sum of infinite terms of GP. So for Sn, when mod r was greater than 1, that is the common ratio was greater than 1, the formula for Sn was a into r raised to n minus 1 upon r minus 1, and the same Sn was equal to a into 1 minus r raised to n upon 1 minus r when mod r was less than 1. Now, for going to sum of infinite terms, that is there are infinite terms in the GP, then how to find the sum of those terms? When I say infinite terms, can I say that the nth term or rather n will be infinity here, correct? So let us begin. That is n is tending to infinity or n is trying to reach infinity. As infinity is not any particular value, infinity is a absurd or imaginary concept. We can say n, we cannot say n equal to infinity. We will always say n tending to infinity. Now, let us take both the cases of r where r is greater than 1 and r is less than 1. Now, when r is greater than 1, so for n tends to infinity and when I say modulus of r is greater than 1, then r raised to n, correct? We have r raised to n in the numerator. For when n tends to infinity, the positive value of r, which is greater than 1, then r raised to n will also tend to infinity or will also become infinity, correct? So when r raised to n becomes infinity, this entire value will be undeterminable. That means we will not be able to determine the value of Sn for n tends to infinity and when mod r is greater than 1. So in this condition, sum of infinite terms does not exist because r raised to n becomes infinity. Let us consider the second condition where mod r is less than 1. In this condition, for n becoming infinity and mod r less than 1, when mod r is less than 1, for example, let's say 0.8, 0.5, 0.02, etc. When I say r raised to n, what will be the value of r raised to n when n becomes infinity? For r less than 1, r raised to n for n tends to infinity will be approximately equal to 0, or in fact we can say that it will be equal to 0, correct? Now when this is 0, now if we substitute this in the formula for Sn, that is a into 1 minus 0 upon 1 minus r, that will be a upon 1 minus r, then I can say that summation from r is equal to 0 to infinity of tr will be equal to, as I said, 1 minus 0, that this will become 1. So numerator will be only a and denominator will be 1 minus r. So this will be your formula for sum of infinite terms for a GP. That will be equal to a upon 1 minus r. Only applicable for r less than 1. For r greater than 1, sum of infinite terms does not exist. Let us take one example in this case. So here we have taken one example which is asking us to find sum to infinity of the series 1 plus half plus 1/4 plus 1 by 8 plus 1 by 16 and so on till infinity. Now if you observe this series carefully, we know that 1 multiplied by 1 by 2 will be half, multiplied by 1 by 2 will be 1/4, multiplied by 1 by 2 will be 1/8, multiplied by 1 by 2 will be 1 by 16, which I can say that the common ratio r here is 1 by 2 and the first term is 1. So I can say here, since r is positive, mod r will be same as r, which will be equal to 1 by 2. So I have a as 1, mod r as 1 by 2. The formula for sum to infinite terms or sum to infinity is, for a GP, a upon 1 minus r, correct? So our a is 1, r is half, so I can say Sn is this, if you solve, will become equal to, thus you know now how to find the sum of infinite terms of a given GP. Here the sum of infinite terms of the GP 1, 1 by 2, 1 by 4, 1 by 8 dot dot till infinity is nothing but equal to simply 2, right? Let us now see the application of geometric progression, that is GP, for expressing recurring decimals as rational numbers. We have already learned in previous standards how to express recurring decimals as rational numbers using some basic operations. Now we can actually express recurring decimals as a GP series and then find sum to infinity to convert it into rational numbers. Let us see how do we do that by taking few examples. Let us take our first example. So 0.6666 dot 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 is my recurring decimal. Now, how to convert this recurring decimal as rational number using GP, sum to infinity of GP? Let us see. I can write 0.6666 as, I will split it and write like this. Correct? So what I have done is, I have written 0.6666 dot dot as 0.6 plus 0.06 plus 0.006, which will add up to form the given number, our original number. Now if you see this split series, this is nothing but where first term is 0.6, and if I multiply 0.6 with 0.1, it will become 0.06. Further, if I again multiply by 0.1, it will become 0.006. Again multiply by 0.1, it will become 0.0006 and so on. So I can say that this is a sum of terms of geometric progression, that is GP, and we are going up to infinity because this is not ending, correct? Recurring means up till infinity. So I can say this is a GP where A is 0.6 and my R is, or rather I can say my mod R is equal to mod of 0.1, which is nothing but 0.1, which is less than 1. So my mod R is less than 1, which means I can find sum to infinity for this given GP, because we know that if mod R is greater than 1, sum to infinity cannot be found. So let us find the sum to infinity. What is the formula for Sn up to infinity for a GP where R is less than 1? Sn is equal to A upon 1 minus R. My A is 0.6, my R is 0.1. So let me write down. If I simplify this, I will get 0.6 upon 0.9. If I multiply by 10, I will get 6 upon 9, and 6 upon 9 if I reduce, I will get 2 upon 3. So therefore I can write So I have converted the recurring decimal 0.666 into rational number, that is 2 upon 3. Let us take one more example to convert recurring decimal into rational number using sum to infinity of a GP. So let us take the second example. .5 bar. What is 2.5 bar? That is 2.5555 till infinity. So I can write this as like this. Now this can be split into addition as follows. Correct? So what I have done is 2 plus 0.5 plus 0.05 plus 0.005 plus so on. Here we see that after the first term, the remaining terms, that's 0.5, 0.05, 0.005 are in GP with their first term as 0.5 and the common ratio as 0.1, because if I multiply 0.1 to this, I get the second term. Again, I multiply 0.1, I get the third term. So can I write the GP as first term A 0.5 and mod of R as mod of 0.1. that is 0.1, and 0.1 is less than 1. So yes, I can find sum to infinity for this GP. Correct? Because sum to infinity is found only when the mod r is less than 1. It is not applicable for mod r greater than 1. Therefore, Sn will be a upon 1 minus r. That is the formula for sum to infinity of a GP. A is 0.5, r is 0.1. This will further simplify to 0.5 upon 0.9. 0.5 upon 0.9, that is nothing but 5 upon 9. So my Sn is 5 upon 9. Now this is sum to infinity from second term onwards. Plus we want to add the first term, that is 2. So I can write 2.5 bar as 2 plus sum to infinity, which if you simplify, you will get the answer as. So I have converted 2.5 bar, which is a recurring decimal, into a rational number, which is 23/9. That's our final answer, converting recurring decimal into rational number.
Subscribe to my channel. Click on bell icon to get notification about new video.